If two events are independent of each other, then the first probability has nothing to do with the second one. It has no impact whatsoever on its probability. And if two events are dependent of each other, then one clearly depends on the other. Event B depends on what happens in event A because something will change in the sample space. And let's look at these two situations here. All right? Disregarding their political correctness, let's talk about them. All right? So, like we said, every single toss right here has no bearing. First toss has no bearing on the second toss, and the second toss has no bearing on the third toss. So every toss would be 50% for heads or tails. Now, over here, I've got 5 girls waiting to be asked to dance by 3 boys. So if I'm looking at this situation, okay, I've got the 5 girls here. Of course, a boy comes up and asks a girl to dance. How does that change things for the next girl? All right. There's one less girl to choose. Like, from the girl's point of view, there's one less guy to choose her. And from the guy's point of view, there's one less girl to choose from. The sample space changes. So the probability of B, the second girl being picked, changes after the first girl was chosen or asked or whatever, right? So that's how things are different there. This first situation, the sample space keeps changing. Every time you draw another name out of the hat, someone else is left different. So whereas the first one would have been 1 out of, say, 25 people in the class, after that first person's gone, it becomes 1 out of 24. And then the sample space changes again, and it'd be 1 out of 23, etc., etc. So the sample space changes. So this is dependent. This is a dependent situation. Okay? Now let's go to the beach. Let's take a weekend at the beach. You're sitting on the floor. Your parents say you got 2 days at the beach. I need you to pack a bag. So you're sitting on the floor. You got your bag. Your drawer's up behind you. You don't look. You just reach up behind you, grab a pair of socks, reach up again, grab another pair. So you've grabbed 2 pairs of socks, right? Pair of socks. Okay. So you reach up and grab a pair of socks. Stuff it in your bag, reach up and grab another pair of socks, stuff it in your bag. Okay? Now, is this an independent or dependent situation? Remember, we didn't say this, but your favorite pair of socks was in that drawer somewhere. Okay?
Are you trying to take the favorite pair of socks?
Well, that would be a natural question, right? Do you get your favorite pair of socks or not? Remember, we didn't look. We just reached up there and grabbed it randomly.
Well, if I was going to the beach and I wanted my favorite pair of socks, I would.
Okay? So, as we're looking at this, the probability of 2 independent events is going to be the probability of the first event times the probability of the second event. Okay? It actually works for most of our compound events. We multiply probabilities together. Now, the word "and," I'd like for you to remember this from last week. A and B. I want to use that intersection symbol because you're going to see that frequently. So we want to make sure we recognize the intersection symbol as meaning "and." Okay? So the probability of me having 2 events happen in a row, if those events are independent, I just simply multiply the 2 probabilities together. Let's go back to the example we did last week with the coin flip 3 times and finding out the probability of all heads. Now, last week we drew the sample space with a tree, right? So we'll do that again real quick. So using our tree from last week, heads, heads, heads only happens once, and there's 1, 2, 3, 4, 5, 6, 7, 8 different ways, combinations this could happen. So it was 1 out of 8. Now what I want to do is this. On a small sample space,
What's it called when you put the number factor, like the power to the power? Okay.
that one would be an exponent.
It'd be,
1/2 to the 3rd power.
If you flip the coin 10 times, it'd be like 1 over 2 to the 10th power.
Yes, that is right. Okay?
All right.
All right. So guys, of course, because this sample space would be way too tedious for 10 times, now I need to focus on my rule. These are all independent flips. So the first one is 1 out of 2. The second one is 1 out of 2. The third one is 1 out of 2. The fourth one is 1 out of 2. And so on. How many times does that happen? 10 times. So it's going to be 1/2 to the 10th power. But that 10th power really comes from multiplying over and over and over again. And what does that give me? 1 over, I think it's 1024. Okay. And of course, you could change that to a decimal. If you'll go ahead and change that to a decimal and a percent, you'll see exactly how small that is. It's less than, I think it's less than 1,000th of a percent. It's very, very small. On the candy. All right. So those things are independent of each other. So the 5 Mountain Dews would be 5 Mountain Dews out of 10 possible drinks times 4 pieces of gum out of 12 possible pieces of candy. But you see that the candy had nothing to do with the drinks, and the drinks had nothing to do. So this is independent. So of course you just multiply and you get 20 over 120. Is that right? Yeah. Which is 1/6, which whatever percentage that is. So obviously that should have been 5/15. 5/15 right here. Sorry. And then of course that changes. So that was my fault on the arithmetic there. We know it's independent because this first drawing and the second drawing have the same exact sample space. So what is the odds that, or excuse me, what's the probability that she chooses red the first time? There are 6 out of how many? 11. And what's the probability she chooses red the second time? 6 out of 11 again. And what do you do with those two? Multiply. So this is going to be 36 out of 121. Which is basically what? 30? All right. Okay. This B line A doesn't mean divide. Don't think it's divide. It's the probability of B given that A has already occurred. In other words, the sample space has changed. But other than that, these are still compound events, and you still multiply. So really, it's about the same thing. Let's talk about a deck of cards real quick. Okay? It is assumed that an American teenager knows how many cards are in a deck of cards. So let's review some deck of card rules. All right. This is a dependent situation because once you draw a card, the deck has changed. It goes from having 52 cards in it to now only having 51 cards in it. So I still follow my probability rule the same. These are still compound events. I'm still going to multiply, but my sample space has changed. So what is the probability on the first card that I get a heart? How many hearts are there? There are 13 hearts out of 52 cards. Or some of you might have went ahead and abbreviated that as a fourth, right? Okay. So the first heart, or excuse me, the first card could be a heart 1/4 of the time. 13 out of 52. Now the second card. How many hearts are there? That's right, there's only 12 because I've already used one of them. And how many cards are in the deck? There's only 51. See how things have changed? So the second event depended on what happened on the first event, didn't it? So this is a dependent situation. You still do your probabilities the same. You go ahead and multiply. And I have no idea what that is. Let's run that. So that right there, but if it's 1 out of 17, it's about 6%. That's considerably lower than the 1/4 that you thought it was probably going to be, right? Because you thought, hey, there's a fourth of those cards are hearts. Okay, it's actually a lot lower. Which is why drawing 2 hearts in a row, say to get a flush, you know, that's why flushes are ranked higher, because the probabilities are lower. It's harder to get. All right, now let's look at about the aces. Is this an independent or dependent situation?
Dependent.
It's dependent because as soon as you choose one card, if you don't put it back, you have changed the sample space. So what are the probability of getting that first ace? There are 4 aces in the whole deck, so there are 4 out of 52 are aces, right? Now, after you chose that first ace, how many are left? Yeah, there's only 3 to choose from now, right? And there's only 51 cards left in the deck. So let's run that number, 12 over something. Okay, so I probably rounded wrong, but 0.004, which is 0.4%. That's less than half of 1%, right? Very small probability of getting 2 aces in a row.